morning or good evening. My name is Kanji Mori from National Astronomical Observatory of Japan, NAOJ. And today we are happy to invite Professor Miho Ishigaki from NAOJ. She got a PhD degree at Tohoku University in 2010. And after that, she worked as a postdoctoral researcher at NAOJ at the University of Tokyo and Tohoku University. And from 2020, she's working at NAOJ as an assistant professor. And she's an expert on spectroscopy of metal plus stars, and she's working on chemical and dynamical evolution of the Milky Way Galaxy. And today, she's going to tell us about the origin of metals in the universe and implications from all the galactic stellar populations. And in this talk, you can make quick questions even during the talk. So in that case, please just speak up. And but of course, we will have the time for questions after the talk. So you can make questions there too. Okay, so Ishigaki-san, now the stage is yours.
Yes. So I first would like to thank the organizers for hosting such a great series of seminars and having me today. So if you are involving the observations of galactic stars, you would agree that now is the exciting time where everyone has access to huge databases of galactic stars, including stellar motions, stellar positions, stellar surface chemical composition, and even ages. So I'm personally also involving one of such projects of observing galactic stars, especially the old galactic population in the outer part of the Milky Way, using a new multi-object spectrograph developed at Subaru Telescope, which is called the Prime Focus Spectrograph, or PFS. So in this talk, I would like to share with you the prospects of using such data from huge large surveys to infer about the origin of metals in the early universe. And here is my collaborators, especially would like to acknowledge the continuous discussion with theoretical astrophysicists. So I think as we all know, metals, meaning the elements heavier than helium, constitute very tiny fraction of the universe, while it is essential ingredient for planets and life. And therefore, the origin of metals is one of the important and outstanding questions in all the scientific field. And I found interesting and excellent review talks in this IRENA seminar series as well regarding the origin of metals. So the diverse chemical elements we see today, basically the end product of the cosmic chemical evolution, driven by many generations of stars and their explosions. So as we go back in time, the universe was less enriched with metals, and within a few 100 million years from the Big Bang, there was only pristine hydrogen helium gas without any metals heavier than lithium. So why do we specifically care about the metal production in the early universe? So the metal enrichment sources in the early universe are of particular interest in many respects. The first, the nature of metal enrichment sources in the early universe can be very different from what we see today in the local universe. The most obvious example is the first stars, or population 3 or POP3 stars in the universe, which were formed out of pristine hydrogen and helium gas. Since the cooling of gas is very inefficient in such a pristine environment, the simulations predict that the masses of the POP3 stars can exceed more than a few hundreds or thousands of solar masses. And also in the early universe, the environment to which the ejected metals are dispersed can be very different from the local universe. According to the cosmological simulations, the first stars that are the source of metals for the first time in the universe are formed within a so-called dark matter mini-halo, which have relatively shallower gravitational potential than what we see today in the present universe. So one POP3 supernovae, the kinetic energy from one supernovae can exceed the gravitational binding energy of such halo. And in this case, the ejected metals are escaped from the host halo without directly incorporating into the next generation of stars. So again, simulations predict that such metal enrichment process are very stochastic in the early universe and depend on various different physical conditions realized in the early universe. So knowing such a nature of the first metal enrichment sources and their environment are crucial to understand the galaxy formation in the early universe, because, for example, the masses of the POP3 stars can produce, depending on their characteristic masses of the POP3 stars, they produce different energies of ionizing photons that have contributed to the cosmic reionization. Also, they produce their energy via supernova feedback, which can also delay the subsequent formation of galaxies. So if the POP3 stars were extremely massive, they could be a seed of supermassive black holes at the centers of large galaxies. Also, the metal production in first stars can trigger the formation of dusts in the early universe that are again significantly affect the star formation process for the next generation of stars and the very fast galaxies. So not only the POP3 supernovae, but the mechanism of other more normal types of supernovae has many open questions as well. The snapshot of the cosmic chemical evolution at about 4.5 giga-years ago from now can be best constrained by the solar system abundance patterns, as can be seen today. So we can see that the most dominant metals are the elements from carbon through zinc, and they show characteristic odd-even patterns. So that predominantly come from the contributions from either core club supernovae of massive stars or type 1a supernova of white dwarfs. For both types, the explosion mechanisms and progenitors remain largely uncertain. And in particular, for type 1a supernova progenitor, there are different hypotheses about the masses of white dwarf progenitor. Either they have sub-Chandrasekhar mass white dwarf or near Chandrasekhar mass white dwarfs. So a similar abundance pattern can be seen in the nearby galaxy cluster, and based on the abundance data, which is essentially consistent with the solar system abundances, this work by Simonescu provide the estimate of relative contribution of type 1a among all metal enriching supernovae would be around 13 to 40%, where this range comes from various theoretical different yield models. So the question is how these ratios and relative contributions from different types of type 1a change as we go back in time. So this is the main takeaways from my talk. So in this talk, I'd like to focus on what chemical abundances in old stellar populations in the Milky Way tell us about the metal production in the early universe. I would like to first describe the growing elemental abundance data combined with stellar ages and kinematics, and also highlight how uncertainties in stellar and supernova EID models affect the interpretation of observed chemical abundances. Finally, I would like to emphasize the importance of hunting the old stars beyond the solar neighborhood. So the most promising fossil record of the metal enrichment in the early universe is currently considered as extremely metal poor stars, or EMP stars that have metallicity FeO/H below -3. So once the POP3 star form with masses of a few or several tens of solar masses in the cosmological dark matter mini-halo at a redshift greater than 20, they synthesize metals for the first time in the universe and then eject the metals through supernova explosions. So these ejected metals are diluted with pristine gas, that's including iron. So one expectation is that the gas metallicity can then become FeO/H of about -2 to -3. So the extremely metal poor stars, EMP stars with metallicity below -3, can be considered as stars that are formed out of gas purely enriched by POP3 stars. Therefore, the observed chemical composition of such EMP stars are compared with theoretical yield model of POP3 stars and their supernova explosions. So one of the most excellent examples of how a single EMP stars can have implications about metal sources in the early universe can be seen in this case of SMSS 03136708. So this star was originally discovered by the SkyMapper survey, which is the wide area photometric survey making use of the narrowband filter sensitive to calcium HK line. So the follow-up spectroscopy revealed a remarkable feature about this star, namely their spectra is essentially, there was no iron absorption line found in their spectra. So careful analysis, taking into account the non-local thermodynamic equilibrium, as well as 3D model atmosphere, the conservative upper limit for iron abundance for this star has been estimated to be -6.5, which is a few orders magnitude lower than the previous record of lowest iron abundance star. So another remarkable feature about this star is the highest level of enhancement of oxygen and carbon relative to calcium. So this leads to many interesting implications about what kind of POP3 stars are responsible for observed metals in these stars. So if the metals come from a single POP3 supernova, the observed calcium can be, first of all, it can be either produced from hydrostatic or explosive silicon or oxygen burning. Or this is also the true for normal massive stars in the present universe. So if the POP3 stars undergo highly non-spherical explosion, as illustrated here, the synthesized calcium can be escaped from the progenitor star, while most of the iron just fall back to the central compact remnant. So another interesting hypothesis about the origin of calcium is the breakout reaction from CNO cycle, this can occur in pristine star, and that can burn hydrogen at higher temperature. So another interesting implication is that the observed metals may come from some of the nucleosynthesis occurred as the result of rotational mixing in POP3 stars. Also, if the metals are produced with these specific ratios, there is prediction about what kind of dust can be formed out of ejected metals that can also have further implications for the next generation of star formation. Finally, another intriguing hypothesis is that this star itself can be low mass survivor of POP3 star, while their metals are later accreted to interstellar medium and with this specific abundance pattern. So unfortunately, all these hypotheses are still inconclusive because of the limited number of elemental abundance measurements available for this star with relatively low statistics for this kind of extreme stars. So thanks to all the past observational effort, we have now access to the larger sample of elemental abundance data for EMP stars, as can be seen here. So this is the latest compilation from Hartwig et al. And show the abundance ratios plotted against metallicities. So we can notice several clear features. First of all, the lightest elements like carbon, nitrogen, oxygen have a few orders of magnitude scatter in their elemental abundance ratios, while there is only small scatter for iron peak elements. And not only the scatter, but some interesting correlation can also be identified. And for example, a subset of carbon-enhanced metal posters show remarkable similarity in their elemental abundance patterns. So the question is whether such observed scatters and correlation can be explained by the properties of POP3 stars and their supernova explosions. So in principle, the production of metals in massive stars depend on the basic physical conditions, such as the initial composition or temperature, or the density at which nucleosynthesis occur. So here is an example of calculated abundance distribution after the supernova of one POP3 star plotted against radius in enclosed mass coordinate. So we can see that carbon, nitrogen, oxygen are loosely bound to the progenitor stars that are formed during the hydrostatic burning of stellar evolution, and their relative ratio depends on the progenitor star properties. On the other hand, iron produced through radioactive nickel is more tightly bound to the progenitor stars and have been mostly produced by supernova as supernova shockwave pass through the falling stellar material. So, however, one of the main factors that determines final chemical yields is the hydrodynamical properties of supernova ejecta, which is subject of large uncertainties because of the uncertainties in the supernova mechanisms. So to calculate supernova yield, the simplest assumption is to employ so-called mass cut, which is the boundary above which the material can be ejected to interstellar medium. And below that boundary, the material fall back to the central compact remnant to form a neutron star or a black hole. So, however, this is not a good approximation because of the presence of mixing between the inner and outer layers of the progenitor star of the supernovae. If the explosion is close to spherically symmetric, the boundary between different layers of elements can be subject of Rayleigh-Taylor mixing, as can be seen in the 2D supernova simulations. So if the explosion is highly non-spherical, as commonly observed in the local supernova remnant, the mixing can be much more extensive. So in order to calculate supernova yields, taking into account such mixing effect, we need multi-dimensional simulations, which are highly computationally expensive, and it's challenging to explore a wide parameter spaces. So an alternative approach is to use so-called mixing fallback model, which approximately takes into account the effect of non-sphericity in the supernova explosion. So in the model employs 3 parameters that correspond to the inner boundary of the mixing zone and the outer boundary of the mixing zone and the fraction of this material in the mixing zone finally ejected to interstellar medium. So despite the simplicity, this kind of analytic model allows us to identify what is the most important feature in observed elemental abundances, and that could be ultimately a benchmark for more realistic simulation after we explore large parameter spaces to fit observed abundances. So to illustrate the effect of model parameters on predicted yields, shown here is the dependence of predicted yields, predicted abundance ratios as plotted against atomic numbers by varying the inner boundary of the mixing zone. So we can see that the abundances of iron peak elements largely change as a result of one of the observed EMP stars. So similarly, this is the variation in predicted yields with the outer boundary of the mixing zone parameter. And we can see that there is large variation for elements that are contained in this the assumed mixing zone. So finally, this is the dependence on ejected fraction. We can see that the overall pattern from carbon to silicon are preserved, while their ratios with iron have some variation, which can also be constrained by observations. So thanks to large sample of EMP stars, we can now ask the question about what is the POP3 supernova yield models that can best explain observed abundance distribution in EMP stars. So this is the histogram of the POP3 supernova yield models that best explain sample about a few hundred EMP star sample of element abundances. So we can see that the models that have a progenitor mass of 25 solar mass and have high explosion energy or hypernovae most frequently best explain observed elemental abundances. So for the same model for POP3 star, we can also ask what is the most likely parameter range that can best explain observed elemental abundances. So shown here is the combined likelihood in the parameter space of the mixing fallback. And we can see the concentration in specific region, so which corresponds to the mixing fallback that finally end up with a black hole remnant of mass of 5 to 6 solar masses. So the approach mentioned above is relies on abundance stellar and POP3 supernova eels, which are at the moment highly uncertain. And also there is uncertain assumption about the environment in which those metals are ejected. So among others, the stellar rotation in POP3 stars are known to have significant effect on the stellar evolution itself and predicted yields. For example, the work by Choplin et al. Predict that by changing the POP3 stellar rotation, we can have a wide range of abundance ratios as well as the isotopic ratio of carbon. Also, so far we have only looked at abundance ratios as a main constraint of the model, but it is also important to check whether the absolute iron abundance relative to hydrogen is consistent with the overall yields. And this should be determined by comparing the models that simulate the dilution of metals in pristine gas. So the work by Mag et al. Demonstrate and highlight the importance of the better considering the effect of metal dilution in given supernova to correctly interpret observed abundance pattern in terms of POP3 supernova. Finally, the most obvious shortcoming of this approach is that the assumption that only a single POP3 supernova contribute to observed metals in EMP stars. In fact, many recent simulations predict that the POP3 stars are more likely formed in a binary or star cluster rather than in isolation. So if this is the case, the metals from multiple POP3 supernovae can simultaneously contribute to the next generation of stars. So if the majority of EMP stars are actually enriched by multiple previous supernovae, the inferred properties of POP3 stars would be largely biased. So in order for such a complicated but more realistic scenario, it is the model parameter space would be too large to be constrained by the data for each typically available for each star. So instead, the recent publication by Hartwig et al. Provides a new approach of using a machine learning algorithm to calculate the probability of mono-enrichment based on the observed elemental abundances. So the machine learning model first employs a training set of POP3 supernova yield models for mono-enrichment and multi-enrichment cases. And this is the example of the distribution of the training set in the two abundance ratios of carbon over magnesium and calcium over iron. So the model is trained on not only these two ratios, but all the available abundance ratios for EMP stars. And then with this, given the observed data, the algorithm can calculate the probability of mono-enrichment as shown here in the right hand side. So this is the probability of mono-enrichment in color in the diagram of Fe over H versus carbon over hydrogen. And for 462 EMP stars we collected so far. So according to, for the current set of yield models we employed as a training set, we estimate the fraction of mono-enriched stars is about 32%, which means that remaining 68% are more likely multi-enriched. So, this algorithm still depends on what kind of training set we employ and what kind of supernova yield models are employed, and underlying assumption. This provide important algorithm to interpret the large and complicated data sets from ongoing and upcoming surveys of galactic stars, and taking into account our best knowledge about supernova yield models, and really provide a helpful tool to make the most of data from such surveys. So up to this point, we mainly talked about EMP stars in the solar neighborhood as the probe of metal enrichment in the early universe. However, at the same time, the EMP stars alone cannot probe the general environment in the early universe, because by selection, EMP stars basically probe extremely pristine environment in the early universe. On the other hand, if we look at the high redshift object observation, there was a signature. There's found some signature that wider channels of nucleosynthesis have already operated in the early universe. Also, we also know that the oldest stars in our galaxy, such as globular clusters at the center of our Milky Way, which has age as old as the age of the universe, are not necessarily metal poor. So ideally, to have more complete picture about the metal enrichment in the early universe, ideally it would be ideal to select stars, tracer stars with stellar ages, not with stellar metallicities. So is it possible to select such stars that contain metals from early universe without relying on metallicities? So in general, estimating stellar ages are extremely difficult, and usually we cannot estimate absolute ages with accuracy greater than 20%. But thanks to the high resolution spectroscopic surveys such as GALA, combined with astrometry from Gaia, we have now estimated stellar parameters such as effective temperature or surface gravity and surface compositions for many of the stars in the solar neighborhood that can be compared with the stellar isochrone models to infer relative ages of those stars. So this allows us to select the main sequence turn of stars that are most sensitive to stellar ages with estimated ages greater than 12 gigayears. So also, thanks to Gaia data, we can further select kinematically old halo stars. So in the end, we have selected old halo stars in the solar neighborhood as the candidate of stars belonging to the old stellar population, and look at their elemental abundances compared with supernova yield models. So this is the distribution of the abundance ratios versus FO/H for the selected old halo stars in the present sample. So we can see that there are some chemically and kinematically different subgroups that have been known from previous studies. For example, high alpha stars, shown in blue here, have high alpha over iron and rotational velocity along the galactic disk. So, and also low alpha stars, which have high eccentricity, which is supposed to be the remnant debris of past major event to the Milky Way, which is called Gaia sausage enceladus. Also, the metal poor stars are have relatively small angular momentum for their orbit and tightly bound to the galactic halo. So now, by comparing observed abundance patterns with supernova, different combinations of supernova with models, we try to estimate what is the origin of metals contained in these observed stars. First of all, we test the hypothesis whether a large fraction of those metals come from a single or a few POP3 supernovae. So here is the predicted yield models compared with one of the observation for a single POP3 model. And shown here is the similar model, but with some contamination from normal core class supernovae. So we can see that the abundance patterns are reasonably well explained once we consider additional contamination from normal core class supernovae. But we also found that the iron yields of those models are less than 0.1 solar mass, which is too small to explain observed FU/H of minus 0.6. So in fact, the cosmological simulations combined with semi-analytical model developed by Terumi et al. Predict that for the metallicity range of our old halo star sample and with the age selection of greater than 12 gigayears, the predicted POP3 metal fraction is less than 10% here. And it is not very likely that observed metals in these stars are predominantly come from POP3 metal enrichment. So a more natural explanation would be the combination of normal core club supernovae and type 1a supernovae. So we parameterize the model with the number fraction of type 1a supernovae, as well as the IMF slope and metallicity of the core club supernova progenitors. So here is the example of the fitting to the abundance ratios. So we can see that how the predicted yields depends on the different assumption about the number fraction of type 1a supernovae. As the result, we get this kind of histogram of the fraction of type 1a that best explain observed elemental abundances in old halo stars. So we can see that as for the high alpha and low alpha subgroups of stars, there are models that have the fraction, type 1a fraction of 10 to up to 20% best explain observed elemental abundances. So this corresponds to mass fraction of iron from type 1a of up to 44% of those two subgroups of stars. For metal poor subgroup, we estimate the fraction of type 1a is less than few percent, and this corresponds to the mass fraction of iron from type 1a of 20%. Finally, we tested the different assumptions about the types of type 1a supernovae. So, namely, whether the type 1a progenitor could either be sub-Chandrasekhar white dwarfs or near Chandrasekhar mass white dwarf. So shown here is the histogram of the best fit model, and the rightmost bar corresponds to the model with core class supernova only, while the 4 bars on the left correspond to the model, combined model for core clusters and type Ia supernovae, and with different assumption about relative fraction of near Chandrasekhar mass white dwarf type Ia supernovae among all the metal-enriching type Ia supernovae. So we can see that as for the high alpha and low alpha subgroups, we can see that the models that have both contributions from sub-Chandra and near Chandrasekhar mass white dwarf progenitor, as for type Ia, most frequently best explain observed abundance patterns. So although the nature of type Ia supernova progenitor remain largely uncertain, there is a similar hint from galactic stars and stars in dwarf galaxies that some type Ia from sub-Chandrasekhar mass white dwarf contribute to their metals. So this should further be investigated with larger samples from ongoing and upcoming surveys of galactic stars. Okay. So finally, so far we have mainly discussed about the implications on the metal enrichment in the early universe from the old stellar population in the solar neighborhood. In the future, we will get a much larger volume, the stars from much larger volume in the Milky Way to completely chemically characterize their stellar populations. So these are the ongoing and planned future spectroscopic surveys that can provide chemical abundance data for those stellar populations. So further out to the outer halo, there has been a hint that the outer halo contain more pristine and chemically interesting stars. So it is extremely interesting to go beyond the local halo and identify chemically interesting stars in the outer halo. To this end, I'd like to particularly advertise the Prime Focus Spectrograph at Subaru Telescope, which I'm working for. So the PFS has a unique capability of reaching the outer part of the Milky Way with the multi-object spectrograph with 4,400 fibers over 1.3 square degrees. So here is a very rough illustration for main sequence turn of stars. If it is located at 50 kpc from the sun, the apparent magnitude would be around 20 seconds magnitude, which can be reached by this instrument. So with those upcoming surveys and that probe the old stellar populations in the much larger volume of the Milky Way, we will ultimately be able to capture the true diversity in metal enrichment in the early universe. Okay, so this is the summary of my talk. So I focused on the implications of old stellar populations in our galaxy on the metal enrichment and metal production in the early universe. So I described the growing elemental abundance data combined with stellar ages and kinematics provide new insights into the metal enrichment in the early universe. And also highlighted how uncertainties in stellar and supernova heat models affect the interpretation of observed chemical abundances. But we have prospects of empirically constrain such uncertainties in yield models with upcoming stellar data. So finally, I emphasize the importance of hunting old stars beyond the solar neighborhood. And there is interesting prospects with multi-object spectrograph spectrograph in many different surveys, branch surveys. Okay, so this is the end of my talk. Thank you very much for your attention.